All right, for homework number 16, the first section tells us exactly which test to use. So use the direct comparison test to determine the convergence or divergence of the series. To save a little time, I kept up my compare, known, and DCT little statements just to organize things. So we are comparing our unknown sequence to a known sequence, and you usually do that just by cutting off the extra terms. This fraction has a larger denominator, so it will be smaller than the one on the right. And we know that the sum from 1 to infinity of 1 over n squared is a convergent p-series. Make sure when you're doing this, by the way, I'm pretending that these are free response questions. You need to have your proper notation. You can't just write sigma, or you can't just write 1 over n squared without any sigma. That would be really wrong. Convergent p-series. So have the proper notation. If you practice it in your homework, you'll do it correctly on a free response question. And so since the series that is on top is converging, then the series that decreases even faster will have to converge too. So I'm just going to make my conclusion by saying the original series that we're looking at converges by DCT. All right. For this next one, we are looking at 4 to the n over 5 to the n plus 3. So again, I'm just going to cut off that extra term that's being added. This fraction has a slightly bigger denominator, so it's overall smaller. And we do know about the series from 0 to infinity of, let's make this 4/5 to the n, so it's a little more obvious what this is. This is a convergent geometric series because r is less than 1. And again, the series on top is converging, so that's the one that's decreasing even faster will also converge. So we just make our final conclusion. I get if you're doing your homework and you don't want to write all of this out, but again, if you practice it this way, then you won't feel like you're cramming so much for what you have to do on the test. So converges by DCT. You don't have to show your work this way. This is not like an AP format. This is just the way that I feel like I can efficiently but thoroughly answer these questions and get all the points. All right, next one, we're looking at ln n over n plus 1. So we wouldn't want to compare to 1 over n plus 1 because technically, even though that's a general harmonic, we would have to do integral test to show that that convert or diverges. So instead, just compare it to 1 over n, the terms for the harmonic series, because this is a smaller denominator overall, but ln1, the numerator here is, or ln of n, is going to keep growing. So ln of n over n plus 1 is definitely going to be bigger in the long run than 1 over n. And we know that the series from 2 to infinity of 1 over n, that's a harmonic series. Harmonic doesn't have to start at 1. So this is a divergent. You can either say a divergent harmonic series, or you could also say a p-series. Harmonic is just a special p-series. And then because the series that's on the bottom this time is diverging, if it's not growing, if it's not decreasing fast enough, then the one on top is not decreasing fast enough either. So the original series from 2 to infinity of ln of n over n plus 1 also diverges by DCT. So now I'm looking at 1 over the square root of n cubed plus 1, and I'm just going to cut off the 1, compare it to 1 over the square root of n cubed. This fraction is smaller. And we want to look at the series from 1 to infinity of 1 over, let's make this n to the 3 over 2. So that's a p, a power that's bigger than 1. So this is a convergent p-series. And if that's the convergent p-series and it's the one on top, if there's one that's decreasing even faster, then it's also going to converge. So from n equals 1 to infinity, 1 over the square root of n cubed plus 1 converges by dct. All right, let's take a look at this one. 1 over n factorial. So this is different. There's nothing to cut off here. But you could compare it to just like think about function races that we talked about. Exponentials grow the fastest, and then what's after that? Factorials grow the fastest, and then after that are the exponentials. So you could really make this anything. I thought of like e to the n. It could be 1 over 2 to the n, 1 over 1 million to the n, whatever. It doesn't matter. But I know that the factorial denominator will grow faster in the end than whatever exponential you put down here. So the sum from 0 to infinity of 1 over e to the n, we can make that 1 over e to the n. This is a geometric sequence. The r, the common ratio, is less than 1. So this is a convergent geometric series. For this test, by the way, I don't bother finding the sum of this series because that's not what we care about. It's just the fact that this is convergent. So that means that, again, the one on top is converging. So the one on the bottom that decreases even faster will also converge. So the sum from 0 to infinity of 1 over n factorial converges by direct comparison test. Now, this section wants us to use the limit comparison test, and I would assume that you would do that if direct comparison test doesn't work. I'm still going to set up as if I'm not sure because, again, that's just good practice to get into for the AP test. I have not seen them specifically say on the AP test, use this test to show. You have to know which one to use. So, all right. So for this one, we're looking at 2n squared minus 1 over 3n to the 5th plus 2n plus 1. We should compare that to just cut off the extra terms. It would be like 2n squared over 3n to the 5th. And I know that can simplify. I never simplify it until I get to my known because I just want to easily compare these. Smaller numerator, bigger denominator. This is going to, I think this minus 1 is going to be pretty insignificant, but having an extra plus 2n means this denominator will be bigger overall. So this is a smaller fraction. And let's look at this simplified. This is the series adding terms 1 to infinity of 2 over 3n to the third if I subtract my exponents there. So this is a p series with a constant of 2/3 out in front. So it's a convergent p series because p is greater than 1. And so DCT would work, right? Because this is sitting on top of this one converging. So, but maybe because the different terms make it kind of ambiguous, I guess. So maybe they're having us do limit comparison test. I think for what it's worth, let's go back to our notes for a second. The limit comparison test is only inconclusive in 2 scenarios. So if we get 0, but the known doesn't converge, then that would be an issue. Or if we get infinity and the known doesn't diverge, then that would be an issue. But otherwise, we're pretty much always going to be getting an answer for these. So even if DCT would have worked, limit comparison test, I think, should draw the same conclusion. The reason that direct comparison works is because if you can do it, it saves you from showing this limit work. And I think kind of logically it makes sense too. So I'm setting up my unknown divided by my known. Now let's go ahead and say instead of dividing by a fraction, multiply by the reciprocal of that fraction. I'm using the simplified version, which is here too. You could use this one if you wanted. So what do we have on the top? We have 6n to the 5th over 6n to the 5th. So this is coming out to 1. Now, my limits usually do come out to 1 because when I pick something to compare it to, it almost always has the same coefficients. I'm just cutting off extra terms. As long as you get a number between 0 and infinity, then the two series act the same. So I can say, therefore, the sum from 1 to infinity of 2n squared minus 1 over 3n to the fifth plus 2n plus 1, that also, it acts the same as this p series, so it also converges. So converges by LCT. For our next one, this is a little bit different, right? This 2 to the n minus 1, anytime I see a base number to the n minus 1 or the n plus 1, I want to separate that out. This is 2 to the n times 2 to the negative first in the denominator. So instead of dividing by 2 to the negative first, I'm going to put the 2 up here. And I'm going to do that in my comparison because it will just make life easier. So what I have left down here is an n plus 1 times a 2 to the n. And then the 2 to the negative 1 got moved up here, and there's still an n up there. And I want to compare it to just 1 over 2 to the n. I don't want to compare it to 2n over n plus 1, but I just want to look at the exponential. And I think that this fraction, we could argue that that's bigger than 1 over 2 to the n, because as we take a limit here, this is going to be like saying 2 times 1 over 2 to the n, so it's going to be double. All right, so what do we know? We know the series from 1 to infinity of 1/2 to the n is a convergent geometric series. But that doesn't help us with DCT because the series that's on top is, the series that's on the bottom is converging, and that doesn't tell us about the one that grows more slowly. So this is why we need limit comparison tests. So we take the limit as n approaches infinity of our unknown term. So I'm going to keep it as 2n over n plus 1 times 2 to the n, divided by our known 1 over 2 to the n, but I'm going to make that times 2 to the n over 1. These 2 to the n's would kind of cancel out here, and then you're looking at this limit, which is same degree top and bottom, so that limit is 2. And again, as long as you get a number between 0 and infinity, then the two series act together. So I can say the original problem, the series of n over n plus 1 times 2 to the n minus 1, also converges by limit comparison test. Okay, number 26. We're looking at 5 over n plus square root of n squared plus 4. And what do I want to compare that to? You could just compare it to like 5 over n. Or I don't know if you're seeing that this is going to kind of be like 5 over 2n. You could do that too. I'm just going to do this. So I'm just cutting off like a square in the long run toward infinity. The plus 4 is insignificant. So this is like square root of n squared. So it is kind of like having a 2n under there. There are more terms here. So this first one is a smaller fraction than what I wrote down. And I picked 5 over n because it's a nice simple harmonic series. Not sure what's going on with my pen here. So it's the harmonic series with a 5 multiplied in. So that still diverges. Divergent, harmonic, or you could say p series. Either one is acceptable. Again, the series that's on top, though, is diverging. That's not telling us about anything that grows faster than it. So we need to show limit comparison test. So it's 5 over n plus the square root of n squared plus 4. Instead of dividing by this fraction, I'm going to multiply by n over 5. And then these 5s will cancel. And remember what I said, as n approaches infinity, this really is like having n plus square root of n squared. And the 4 kind of goes away. It's infinity plus 4. It doesn't really matter. So this is kind of like having a 2n down here. So technically, this limit is 1/2. Now, what if it's free response and you say the limit is 1? I don't know. Maybe you get 1 point off for not correctly having this limit figured out, but you would get some points I would assume, for identifying the harmonic series that you're comparing it to, and maybe the correct conclusion. It just depends. All right, so these two things act together because I got a number between 0 and infinity. So the original series in question, this series here, also diverges. So diverges by limit comparison test. All right, last one in this section, we're looking at, this is different, sine of 1 over n. And yeah, what can I compare that to? So think about what those terms are approaching. The limit as n approaches infinity is the sine of 0, and that is 0. And like you would start with, what are the terms? Sine of 1, sine of 1/2, sine of 1/3. I did check this one in my calculator. Let me open this. If I'm ever not sure, I usually default to like the harmonic series, unless I know that I have something like 1 over n factorial, or like something in a clear function race. This is a sine function, is not really clear as far as function races go, because it depends on what part of the sine function you're on. So I was kind of guessing that these two things would be similar. I wasn't sure which one would be larger or smaller or whatever. So I did verify this in my graphing calculator, if it will fire up for me. Okay, while I'm waiting for that, I'm going to write down what I know. So I do know that the series from 1 to infinity of 1 over n, I know that this is, again, the divergent harmonic series. Okay, is this going to open? What's happening? I don't know what's happening with my calculator, but okay, when I did graph these, it did come out where these were actually very close in value, but I think 1 over n was on top. I'm not sure what's happening with this calculator. I don't think it's going to open though. So, okay, it doesn't really matter, does it? Because if I'm going to do limit comparison test, it doesn't really matter what's on top and what's on the bottom. Okay, so let's see what this comes out to. So the limit as n approaches infinity of my unknown, sine of 1 over n, over my known. Now, if I flip this around like I normally do, I'm going to get, if I make it n times sine of 1 over n, I'm going to get 0, if I do that limit, I'm going to get 0 times, or no, sorry, I'm going to get infinity times 0, and that is one of our indeterminate forms. Or if you look at this, plug in infinity, you get sine of 0 over 0, you get 0 over 0. So we need to do L'Hopital's on this one. Now, I do know that sine can only go from -1 to 1. But again, because this is just sine of 1 over n, it's a little bit different. So let's just show this. Let's do an official L'Hopital's rule. This limit is 0, and so is this limit. So I can apply L'Hopital's rule, which says take the derivative. Remember, it's got to be in its rational form. You can't take the derivative of n times sine n. Sine of 1 over n. But the derivative of sine is cosine. And chain rule, the derivative of 1 over n is -1 over n squared. Down here, the derivative of 1 over n is -1 over n squared. And we've seen this before in chapter 8, where these cancel out. And let's try the limit again. When you plug this in, you get the cosine of 0, and the cosine of 0 is equal to 1. So this limit does exist. It comes out to a number between 0 and infinity, so I can say that these two things act together. So the series from 1 to infinity of the sine of 1 over n also diverges, and that's by the limit comparison test. So that's a pretty tricky one. Do I expect that you knew to compare it to 1 over n right off the bat? No, but if we see that again, a sine or a cosine, now we will hopefully remember what to do. Determine the convergence or divergence of the series. So they're giving us the terms here. Let's say this is n equals 1, 2, 3, 4. It looks like it's n times 200 down there. So let's write out the series first. The series from 1 to infinity of 1 over, what did I just say? N times 200, or 200n. This is a quick one, right? This is a harmonic series, so determine convergence or divergence. This is a divergent harmonic series. You can easily pull the 1 over 200 out in front, and it's 1 over 200 times the harmonic series. So, yeah, that's all you have to show. You could say P series as well. 52, the figure shows the first 20 terms of the convergent series from 1 to infinity a sub n, and the first 20 terms of the series a squared sub n. Identify the two series and explain your reasoning in making the selection. When I first read this, I thought like, oh, they want me to come up with a formula for that. But no, they just mean which is which series is on top, which one is on the bottom. If a sub n converges and the series where you're squaring the terms converges, you would think that squared terms would be larger, except notice that like this term right here is at 0.9. If you square that, you're going to get 0.81. And so, yeah, squaring a fraction that's less than 1 is going to result in a smaller value. So the series on top is the a sub n are the a sub n terms, and the series on the bottom, those are the a sub n squared terms. So a sub n is greater than a sub n squared. So identify them, explain your reasoning in making the selection. I think I just explained it, right? So what am I going to write for this? The terms for a sub n are less than 1. Squaring those terms will result in even smaller terms. I'm sure I worded that differently on the key that I posted, but similar idea. True or false? I did not erase my answers for these, so let's just take a look at these. So if sequence A is less than sequence B, and they're both positive, and if sequence A converges, then sequence B diverges. That doesn't have to be true. It might be true, but I came up with a counterexample. What if they're both P series? And, oh wait, this is not... Okay, let me switch this around. Okay, I want to correctly compare these. So the cubed has to be there, squared has to be there, but you get the idea. 1 over n cubed is smaller than 1 over n squared. Both of these are convergent P series. And so that's an example where the larger one doesn't have to diverge. 56, if a sub n plus 10, that just means you start by plugging in 10 here, is less than or equal to b sub n. Or, sorry, you add 10 to whatever you're plugging in when you plug in 1. So the first term in b is like bigger than the 11th term in a. So that just means to me that a is a lot smaller than b, right? Okay, anyway. If B converges, then A converges. And that seems correct, right? That's just saying what direct comparison test says. If the series on top converges, then the one below it's going to converge. It doesn't matter that you're adding 10 every time you plug things in. It's still going to converge because they're telling us this is still less than this one. All right, for 57, if A plus B, those terms are less than C, and if C converges, then the series for A and B both converge. Assume that all three series have positive terms. That has to be true because if either A or B diverged, then the sum of them would have to diverge. If one piece diverges, then A plus B would have to diverge. So, and if that's not the case, if C converges, there's no way that one of them underneath diverges. 58 says A is less than B plus C. A diverges, so the one below diverges, then the ones on top have to diverge. So it's true that could be a scenario, but it could be that B converges and C diverges, or vice versa. It could be that just one of them diverges. So that's kind of like similar to what I was saying in 57. You only need one part to diverge for the whole thing to diverge, for the whole sum to diverge. All right, and then 59, if A is less than B, and A diverges, then B diverges. That's true. That's the other part of our DCT. And 60 says if A is less than B and B diverges, the one on top diverges, then the one on A diverges. That doesn't have to be true. It might be true, but it's false. And that's why we have LCT, because we don't really know what's happening with the one on the bottom. Oh, hey, here's this. Let's take a look. Okay, I'm in radian mode. I just wanted to graph sine of 1 over x and compare it to 1 over x, and maybe not the graph so much as the tables. So we would be starting at 1, so 1 over x is on top, and you can see how close they are. So that was a pretty good comparison. And again, I did not know that off the top of my head that they would be this close. So, you kind of have to use the A to the calculator. I think they would prompt us to do something like that if it were part of a free response question. All right, that takes care of assignment number 16. Let me know if you have any questions.